All right, one more time. If you're just joining us on the Stats GitHub webpage, so Brian Lukov's webpage, sub 371G, click on our help. Under help sessions, there's the midterm 2 review student code. That'll give you the links to the data sets we'll be using for practice problems today, which will save you from typing in long URLs. Hopefully that's on everyone's nice list. Without further ado, Sai's going to kick us off. Han and I will be available to take your questions. If your R code doesn't work for some reason, like you might be missing a comma or a parentheses, we'll be there to help you with that. So you just raise your hand and we'll come around, all right?
Good afternoon, everyone. Today is the midterm 2 review session. We're going to be focusing on multiple regression and prediction intervals, confidence intervals, and pretty much everything that you would be requiring for your midterm 2. Yeah, so let's get started. First of all, what I'd like you guys to do is to open the house's data set. So this is another link if you guys want to type in, or you can go to the GitHub page and copy paste the link from the R code given there. That's going to save you time. So what is the house's data set? Right. So this is a data set that contains the appraised values of houses, the sales price of houses, the square footage of each house, and the number of bedrooms in each house. So what we're going to be using today is multiple regression to predict the sales price of houses using reasonable predictors, using the other variables as predictors, and seeing which predictors are significant in explaining the sales price of the house. Yeah, so how do you interpret the coefficients and the p-values in multiple linear regression? So as you guys know from simple linear regression, in simple linear regression, the slope of the predictor variable is indicative of the amount by which your y increases for a unit change in x. So extending this to multiple linear regression, we can say that the coefficient of a predictor assesses the effect on y of a unit increase in that particular predictor variable when all the other predictor variables remain constant. I want you to run the data set, and yeah, so you can see from the data set that it has all these. Appraised value, the sales price of the house, the square footage, and the number of bedrooms. Hope you guys have done it. Yeah, so how do I determine the statistical significance of a predictor variable from the summary statement? So the statistical significance of any predictor variable relates to the p-value of that predictor variable. So in your multiple regression or even in your simple linear regression, the null hypothesis is that the coefficient of that predictor variable is 0, which means that the predictor variable has no significance in explaining the y variable. And your alternate hypothesis is that the coefficient is highly significantly different than 0. That is, the predictor variable has significance in predicting y. So what range of p-values do you need to accept your null hypothesis and to accept your alternate hypothesis? Anyone?
0.05.
Yes. So if it's above 0.05?
Yes.
I know.
If it's above 0.05, it's not significant.
Mm-hmm.
Below it is.
Yes. So yeah. So that's about that. And that is what we call as statistical significance. But just by looking at p-values, you can say whether the predictor variable is a significant predictor of y. And practical significance from the summary statement. So what is the difference between the practical significance and statistical significance? So the practical significance is the R square, which shows R square for the whole model. The value of the coefficient of the predictor variable is also a measure of practical significance. So I can say that variable x1 is practically significant in explaining y if a unit change of x1 causes a significant change in your y in terms of the values of change in y. So for example, if I have a predictor variable coefficient to be say 0.00001 for predicting the sales price of a house, then that means that by changing 1 unit of that predictor variable, the change in price of the sales price of the house is going to be less than $1, which makes it practically insignificant, right? So that's what practical insignificance relates to. Yeah, so I have some tasks for you. I want you to run the full model first without interactions and determine which predictors are statistically significant and update the reduced model. So I want you to regress. The full model would imply running your y variable as your sales price as your y variable against appraised value, number of bedrooms, and square footage. So you have 3 predictor x variables and you have sales price as your y. We're giving you 5 minutes for this.
Wait, so it's price, price I mean, yeah, you can.
Yes.
What are we predicting?
Sorry?
What are we predicting?
Sales price.
We leave out the house column, right?
Sorry?
The house column.
Oh yeah, so you just leave the first column out. That basically contains the house ID. You don't need that in your regression. So in that case, just because I ask you to run a full model, do not say y tilde dot. If you put dot, then it's going to count the first row as well, the first column as well. So it's better if you type out all the predictor variables. Anybody having troubles running the regression? Please raise your hand. Okay, I assume everyone got that. So that's my full multiple model. It's LM price against appraised value plus square footage plus the number of bedrooms. I'm gonna get this summary for this. Okay, so what do I see from here? Which of my variables, predictor variables, are significant? Which of them are statistically significant and which are not? Yes, so the number of bedrooms, you can see that the p-value is 0.277, which means that it's not statistically significant in explaining the sales price of the houses. So the next step that I want you to do is to remove that variable and update the reduced model.
I'm getting that only price is statistically significant. I'm not familiar with the code. Quick announcement. Several of you have asked me. Yes, the slides, the code, and the video will all be posted after the session.
Well, no, I know. I just wanted to.
Okay, gotcha. Thanks. Great.
And by posted, I mean Canvas and GitHub and YouTube.
I'll give you 3 minutes to run the reduced model.
Add this.
Yep.
So on like practice determined first like 2 questions.
I know.
I can hear you, sorry. So like practice determined like 2 questions. Is that about as long?
The text will be
Yeah. How many questions did the? What's your
I think it'll be this about the same length as the track distance.
Yeah, it's very similar.
Yes. Alrighty. So I hope you guys have drawn the reduced model. So the reduced model would eliminate the number of bedrooms as a predictor variable. So I'm running it against appraised value and square footage, and I'm getting the summary, right? So what do you observe? You can see that the multiple are squared and the adjusted R-squared values have gone down a little. Does that mean that it's a worse model than the full model? Why? Oh, why not? Yes. Yes. Okay, so it's a simpler model, which means that the R-squared value is definitely going to be a little lower. I'm asking you whether it's a better model or not. It is a simpler model, yes. Yes, so that's what is important, right? So you want all your predictor variables to be statistically significant. And if all your predictor variables in the reduced model is statistically significant and still has a multiple R-squared value that's a little less, that's fine. It's still a better model than the full model. All right. Okay, so perfect. How do you interpret the intercept of the reduced model? Here's a summary statement. How do you interpret this intercept estimate 5.538? Anyone? It doesn't mean anything? No. It does mean a lot. So, anyone else? I'll just kidding. Yes.
All variables are held constant. That's
Oh.
your like starting value.
Do you mean zero or constant?
0.
Yeah. So the intercept basically of any regression model, the intercept term refers to the starting value of your y. That is, if all other predictor variables are kept 0, what would be my sales price in this case? I mean, apparently it's $5.53. I don't know why, but yeah. So that's how you interpret the intercept. And how do you interpret the slopes of the predictor variables? Like I said, anyone? Just want to make sure you get the concept right. How do you interpret the slope? Say the slope of appraised value. How do you interpret that? Anyone? Yeah.
For every increase in sales price, the appraised value slope will go up.
No, you got it exactly the opposite.
For every increase in appraised value, the slope will go up 0.67.
Or rather, for every unit increase in appraised value, my sales price is going to go up by $0.67, right? Okay, that's how you interpret this slope of your predictor variables. Any questions? Yes.
Holding what concept?
Oh, okay. Holding square footage constant, right? That's when it's valid. You have to hold the other predictor variables constant. Okay, all right. So next we'll get to confidence and prediction intervals. So in our classes, we've been considering two types of confidence intervals. One using the conf statement and the other using the predict LM statement, where inside you just specify interval equals confidence. So what is the difference between these two statements? What do these two statements do? So the confidence statement basically gives me the confidence interval for a predictor's coefficient, all right? And the confidence interval of the population mean for a forecasted value is given by the predict.lm statement. Whereas the difference between a confidence interval and a prediction interval is that the prediction interval tells you the distribution of reasonable values for a predicted data point. So generally you can expect prediction intervals to be wider than confidence intervals. That is, if I have confidence intervals from 140 to 180 for sales price, then I can expect prediction interval to be wider than confidence interval. All right. So that's another task for you. I want you to find the confidence intervals for the predictors coefficients in the reduced model at 95%. Remember, the confidence intervals for the predictors coefficient is obtained by the confidence statement. Get to the first task and then we can do the other. All right. Anybody having troubles with the confidence statement? Okay, I'll give you 2 more minutes to figure it out.
Oh, yeah, yeah.
Oh, no, they changed.
And always remember that if you do not know what parameters go into a particular function, you just type a question mark, write that function, command enter. It's going to give you what the parameters of that function are. Anyone got it? Can you tell me what the answer is?
Yeah, for which predictor?
Yeah, the predictor coefficients, confidence intervals.
For both predictors or one?
Yeah, just let me know. Like, what's the range generally?
I'm sorry, like
For both the predictors, yes.
unit appraised value is 0.5561 for the lower bound, or 0.5562,
Mm-hmm.
and for the upper bound it's 0.800.
0.556 and point. Is that right? Okay. Getting a different answer. Okay, and that should be good. All right. Yeah. So that's the statement. It's confident of the reduced multiple model or whatever you named your reduced model to be. A level equals 0.95. Yeah, that's gonna give me 0.556 to 0.800 for my appraised value, and 1.4752 to 2.831. You might observe a couple of questions that says just asks you for the value of the lower bound or the upper bound for that particular predictor variable, and you just need to give that particular value in that case. Any questions? Okay. The second task is to estimate the sales price for the house as okay, so which is appraised at $150,000 and is 2,500 square feet. And I want you to give a 90% prediction interval for the same house. Hint, use the predict.lm statement. Anybody having troubles with the predict LM statement? Raise your hands. I'm gonna give you 3 more minutes to solve that one. Yeah. Any questions?
Yeah, so it's just a difference in syntax. We can use a value for every single. Yeah. Yeah. So instead of changes either change syntax away.
Anyone having troubles with the predict LM statement?
Yeah.
Alright. So okay, so there are 2 ways of doing this. One is to create a data frame outside of the predict LM statement and add your appraised value and your square footage to that data frame and call that data frame inside the predict LM statement. That's one way. Or you can directly write the predict.lm statement, the model, and new data equals list of your data frame. You can add the data frame inside the predict LM statement as well. I've done it outside over here. So this data frame now has an appraised value of 150,000 and square footage of 2,500. And yeah, so I give a 90% prediction interval for this. The fit gives me the actual value, and the lower and the upper give me the confidence intervals at 90%. Any questions? Oh. Any questions? Yeah. Sorry? Level. It's just level, yeah. That's why, so the interval equals prediction takes care of whether it's a confidence interval or a prediction interval. The level is just the level of significance.
Yeah.
Yes. Oh, okay. So, if you observe this data set, everything is in thousands, right? So, yeah. Or make sure you see the data set properly. You can see that the appraised values are given in thousands of dollars. So it's just 150 point or whatever that is. So if you're gonna enter appraised value equals 150,000, you're gonna get a crazy interval.
Is it okay if we make the text a little bigger for those in the back? Does that work for you?
Yeah. That's fine.
Okay. Thanks. Sorry.
Okay. I want you to do the third task now. I want you to consider the house, same house. Now the house undergoes expansion and 500 square feet are being added. I want you to predict the change in sales price because of this expansion. This can be done manually, but it's painful. So I recommend that you use a difference in two different predict LM statements and subtract the two to find the difference. I'm gonna give you 2 minutes to figure it out. Maybe a little more than that. Oh, fit is the mean value.
So I guess we keep the SSD for values.
Anyone having trouble? Raise your hand, please.
Does the prediction and like level fuzz or that off? I don't know. I mean, it might just be like that. Oh, so you did minus?
I just copy.
I know. I suggested 25 to 30. I mean, I said also,
I'm going to give you 2 more minutes to figure it out. You have a question?
yeah. I think it's something about.
I hope you guys did it. Right, okay. So, for predicting the change in the sales price, I'm going to add another data frame that has appraised value equals $150,000 and square footage equals 3,000. So that's a new data frame. I'm going to run it, and so what am I doing here? I'm printing 2 predict LM statements over here. Predict.lm of reduced multiple model with the new data frame, which has those extra 500 square feet. minus the predict LM from the previous data frame. So the difference of these two should give me, so it gives me 10.768, if you can see over there. It gives me 10.768. So it means that a change of 500 square feet to that particular house increases the sales price of that house by $10.76 thousand. I'm not sure. Yeah. Any question? Any questions? Yep. All right, so that's it for the houses data set. I'm going to give it over to Han. He's going to be explaining a lot more with another data set. Maybe I show.
So how do I go to the art?
3 fingers.
3 fingers? Okay. Oh, so okay.
You
Okay.
might want to minimize. You might want to minimize the size. It's a
The-
little inconvenient because you're going to be plotting a lot, right?
Yeah. But I mean, yeah. All right, guys. So if you don't have any other question, I will be moving on to the next topic. Yeah. So the data set is what we use in the homework. So first of all, I would like you to just load the data set, because every time you saw a new problem, so you better just load the data set, and then we do the view to see the data set. Right. Let me load the data set. Right, from the data set, we see that we're not just having some numerical data, like the population, like the income, like the illiteracy. That's numerical data, which means that the order matters. But we also have some other data set, just like the size. M means media, L means large. So this value is we will record categorical data or dummy variable. Just like the zip code, right? There's no, I mean, doesn't make any sense when you compare with two different zip code. If it's like larger or smaller, so there's no reason to do the comparison because the order doesn't matter. So we have to use another way we call dummy variable to deal with this categorical data. Right. So first of all, whenever you see a new problem, a new data set, you better check to figure out if this column is for numerical, if this column is for categorical data. Right. So yeah, so definition of dummy variable is we take the value 0 or 1 to indicate the absence or presence of some categorical effects. So I would like you to, similar to the homework, do a box plot of the income versus the size. And I think you'll be able to see the same plots that I have. So from the plot, we see that the different category L, M, S have different mean value, which means that we should deal with them separately. So how are we gonna build our model? Right. So let's try to predict the income using the size. That should be pretty straightforward. You just build a model equals to LM and income, size, and data equals to state. Previously, some students asking the question, they have some problem when they try to build, for example, when they build like state, dollar, income, tilted, state, dollar, size, and when they do the prediction, and they have some problem. So I suggest you guys just using this form, using the name of the y variable, x variable, and comma, and data equals to the data set name. Right, so once you finish that, right. So let's do a summary of the model, and you can see we have 3 coefficients: the intercept, the size m, and size s. So we're using size. We have 3 different values, L, M, S, and we end up with 2 variables, size m and size s. So what that means? So size m is either equal to 0 or 1, and size s is equal to 0 or 1. So if we're referring to the reference level, which is size L, size m and size s need to be all equal to 0. And if you're referring to size m, size s need to be 0. And size m need to be 1. And if you were referring to size s, of course, size s equal to 1 and size m equal to 0. Right. So, and also there's no like when you interpret the coefficient of size m, there is like no unit increase of size m because size m is only 0 or 1. So that's something that's different from the numerical data. Right. Once you build the model, you can interpret the coefficient. And so can somebody tell me what's the meaning of coefficient for the size s? What's the meaning of 29.22?
If the state is small, then it's the income goes up by 29.2.
Compared to what?
If that's not M or it's not medium or large.
So yeah, well, partially correct. So first of all, we have to compare with the reference level, right? And the reference level is L. So which means that if size m and size s equal to 0, the reference level will have income equal to the intercept, which is 4,700. And now we have size S equal to 1, which means that we change the size from L to S, and the income increase by 29.22. So that means compare with the reference level, compare with L, if the size is equal to S, the income will increase by that coefficient. So that's the point. So always compare with the reference level. So that's a dummy variable. And the next topic will be the interaction. In the slides, we have built the price equal to beta 0, which is the intercept, plus the beta 1 times living area, plus beta 2 times fireplace yes, plus beta 3 times living area times fireplace yes. So the fireplace is also a dummy variable, right? Because that's yes or no. And the beta 3 is the coefficient for the interaction term. So the interaction term, by definition, that's the product of two variables. Here is the living area times the fireplace yes. And the coefficient is called interaction effects. And the coefficients for beta 1 and beta 2, we call it main effects, because that's the separate. We only see the beta 1 associated with living area, beta 2 associated with fireplace yes. So a very important thing is, if the interaction terms has a dummy variable, what does that mean? That means that we, in terms of the fireplace yes or no, we have to build two separate models. So we have to build a model when the fireplace is yes, and we have to build another model for fireplace is no. And that has been taken care of by the interaction term. So that's a point of interaction. And you have seen other interaction, like the size. Let's say, okay, you want to predict the house price using the length and also using the width. And you can introduce the interaction term of the length times the width. So that's another interaction, but just means that maybe the area itself is also important, so you introduce that. But this is different from the dummy variable. Right, so using the state dataset, and let's try to practice that. So let's build a linear regression model to predict the income using illiteracy and murder rate. These two are numerical. And also we want to build a linear regression model to predict income using the size, which is categorical or dummy variable, and size with population and their interaction term. Right, let's do that. Building a model include the main effects and their interaction effects will be model 11, income illiteracy times murder. And let's see the summary. Right, you have 4 terms: intercept, illiteracy, murder, and illiteracy column murder. Yeah. And the second model is income as a function of size and population. You have seen more term because the size is a dummy variable. It has L, M, S. So we have size M, size S, which is all 0 or 1. And we have population. So the 3 terms are the main terms. And then we have size M times population and size S times population. Right. So once we got the model, we want to see how we can use that to do the prediction. So the question is, what's the effects of a unit increase of the population for the size equal to L? Let's say you have an unit increase in your population, and the size is equal to L. And how does that affect your income? I mean, one way you can do just writing down all the coefficients in your equation, and you can subtract them. Another way is you use the prediction. Yes.
Is it just the population coefficient of negative 1.91?
No, not just that.
If it's large,
If it's large, oh, let me see.
if it's large, then everything else is.
Okay, yeah. In this case, yeah, you're correct. Yeah, but if it's smaller, that you have to do the calculation, because the small is including not just the size S and also size S times population. Yeah. Right. So the easiest way is just you do create a prediction function. Let's predict, plug in the model, define a list, size equal to L. Remember to put the L in the double quotes, right? Because that's dummy variable. That's a name. L is not like just a letter. So put them, even you see like 301, if that's a dummy variable, you should put in a double quote. And population equals to 101. And the interval equal to prediction. So that's a prediction when population equals to 101. And you minus the prediction when you set the population equals to 100. So that's the unit increase in your population on the income, on your Y. Right. Sorry.
Can I see that R script again?
Sure. Can I run that? Yeah, sure. So minus 0019, right? Let's compare with the so that's the same as the coefficient for the population, sorry. Yeah, so you're right, yeah. So that's exactly the same, but for size M or size S, that would be different because you have that size M and size S in the interaction term.
Sorry, we go back to this one more time.
Sure, yeah. It might be easier. So basically, you have two predictions. One prediction set the population equal to 101, and another prediction set the population to be a unit decrease, and you subtract them. If they ask you for an interval, prediction interval, right? You set the interval equals to the prediction. So that's the uncertainty associated with the y, with the income. And we do the
I mean, well, yeah, the idea is using this predictive. I mean, that stuff was a mess if it wasn't like in the context. Yes. I was confused for a second when I was saying this earlier.
right. If you don't have questions, I will be hitting next topic will be the assumption for the linear regression models. So actually, we talk about in the simple linear regression, but I want to say again. So we have four assumptions. The first is linearity. So that means that we assume that the relationship between the x and y holds a linear relationships, which means that the residual has no nonlinear correlation. We will see that again. And the second one will be the independence. So data points are sampling independently. Because later on, when we deal with the time series data, we know that this is not valid for the time series. But now we're just assuming that all data points are sampling independently because we cannot check from the plots. And normality, which means that just the residual are normally distributed. And homoscedasticity or equivariance, which means that the variance of the residual doesn't change with the x-axis or the fitted value. So when we build our model, right, so let's see the differences of the two plots. So when we build our model, let's call it MOD, and we can use plot MOD, and it sort of give us four type of plot. And the first plot can tell us whether the data sets follow the linearity. And so the plots on the left-hand side, you can see no matter what the data set itself, the residual itself, or no matter what the red line itself, there is no distinguishing patterns in that. But we do see some nonlinearity on the right-hand side, because that's a plot to show the first one that has the linearity, and the second one doesn't hold the linearity assumption, right? And then the second part is the QQ plot, so which shows you whether data sets follow the normality. So we have seen the two plots here. On the left-hand side, it showed a good for the linearity. Well, we don't expect all data sets are following in a straight line, but typically most of them follow in a straight line. Of course, compared with the case one, the second one, we have a badly shaped distribution, which means that the normality is violated. So maybe in the test, you're asking about, okay, do I have the violate of the normality? And later on, you may be asking, how do I transform? how do I reduce this normality things? That would be Jerry's topic. Equivariances, right? You see, it's the same plot as the first when we're checking for the linearity. So basically, you see horizontally, the variances are almost the same, but the right-hand plot you show different differences in their variances along the x-axis.
Is this one where we're looking for fanning?
Looking for
Like fanning?
yeah, you can. I mean, but just looking at
That
the.
would like not. That would make it not like pass or like.
I mean, just different. I mean, you have different shape of the non-equal variances, but the equal variances one is where you sort of have the same. I mean, aptitude or distribute along the x-axis. So pretty much like a straight line. Yeah. Yeah. So that's it for my part. Where's Jared? Maybe we can have 5 minutes rest.
Actually, the third dressing first.
Oh, it's okay. Maybe just take 5 minutes. Yeah.
Let's take a 5-minute break and we'll start up again at whenever 5 minutes from now is. 3:03. Everything's on YouTube. So we'll be on YouTube.
So you see equal variances like this, right? So we've upped the zero level of and throughout from here, from left to right, you see that you can actually fit parallel lines.
Oh, okay. Gotcha.
Right. You know what I'm saying? The residuals are not like sloped towards or not exploding or anything.
And then so for normality,
No, it's better to use that. Or plot the histogram of the residuals.
Okay, and then for linearity
Yes. Like I said, if the residuals are randomly distributed, then you don't see any kind of a pattern. You see a pattern over there. Generally, the
this
pattern.
red line.
Exactly. Red line looks great. Yeah. This is like a fairly good line.
Right. Okay. Thank you very much.
Jared? Yes.
Sure. Absolutely.
You gotta start early. I think last time the slides
All right, let's get started again in 2 minutes. It's your 2-minute warning. All right, let's get started. Restarted. So for my section, the practice problems will be from the CARS data set. So not actually one you've used on a previous something, simply because I like this one. Okay. So you should have it in the student help folder. Should have a link to the URL. You can download this, or just use that code line. All right. So I'm going to take an intermission from the slides to discuss further what Han mentioned and talk about how to diagnose your regression plots. I don't know about those guys, but I bet the same thing is true for their TA hours. A common question we get is this normal? You know, I've got this QQ plot, it's kind of bendy. How bendy is okay? So, this will cooperate. All right. Normality we sometimes discuss as being diagnosable with either a histogram or a QQ plot. So for our demonstration, it'll show you both. Is that normal? How can you tell? It's skewed to the right, right? Fold and tail this way, it's skewed to the right. You can tell that on your QQ plot because on the right side, the points start running away from the line. That line represents values fitting the quantiles of a normal distribution. So it's violating that principle on the right side. Okay? That's the connection between the histogram and the QQ plot. All right. How about this one? Is that normal? Is it normal enough? Yes. This is literally generated from a random normal distribution. The trouble is there's only 20 data points. It's a small sample. If I do this over and over again, you'll see a different 20 data points every time. just to give you a sense of what these plots should look like for normal data. This is normal data, as close as you can be, right? But when you have a small sample size, the points on your QQ plot and in your histogram are going to be a bit wiggly, right? You have to be a little more lenient when there's not much data. What if we up the sample size to 50? That probably looks more like what you were expecting, right? I chose 20 and 50 kind of arbitrarily, but I think here you get the point. Notice in the QQ plot, yeah, we've got some points that don't quite fit in the tails, but it's not so bad. I don't have a better way to describe it than that, but the points generally are trying to follow the line on average. Does that make sense? Demonstration's sake, can you guys even see now that I'm standing right in the way?
No, you're great.
Okay,
You're
good. This one does show a little trail. That would worry me. But like I said, these are totally randomly generated. All right, let's up the difficulty a little bit. Are these normal enough? It's all from the same distribution, just differently random. That one's got problems. All right, this one is on the borderline between okay and not okay. So if you were to take this on an exam, and I hope we don't give you something in such a gray area, right? But for the most part, it looks okay, right? The points aren't, there's no pattern pulling the points off the line. All right, one more demonstration of normality. Would you call the histogram normal or normal enough? Would you call the QQ plot normal? No. All right, these are tails that are clearly diverging in pattern. After some point, there's clearly, on average, the points are not near the line. Right? Sometimes you get like a little wiggle in the tail. That's fine as long as they're not trying to steer away from what should be normal. Any questions on detecting normality? You feel a little better about QQ plots? You feel about the same? It's okay too, I guess. So let's talk about homoscedasticity, or in other words, equivariance. Do these points have equivariance? All right, good. We're starting from a place of common concern, or of common knowledge. Do these points have equivariance? No? Good. I don't know why I keep stepping to the side. I guess I keep thinking people can't see. How about this? Pretty close. Sorry, you probably wanted a better answer than pretty close. I tried to construct this one to be right on the borderline between what you would be okay with and not. If it looks like this, I would be okay with it generally. How about that? Or that? As you can probably cheat and look at the code, this is equivariance by explicit definition. There is nothing, no funny business going on. This is exactly what it should look like to be truly equivariance. Notice, though, every time there's a couple points that make you cringe. Right? But generally, between plus and minus 2 standard deviations, we have how much of the data? 95%, right? Outside of plus or minus 3 standard deviations, or inside of plus or minus 3 standard deviations, we have about 99.7%. Meaning with a large enough sample size, or just random chance, you'll get some of these guys that will look like outliers, but are really just okay. Fortunately, this guy doesn't look like he's way too out in the boonies, so. But just to give you further demonstrations, I keep clicking through these because the more you see, I feel, for at least me, it gives me an intuition of, all right, here's the pattern. If it looks enough like that, we're good to go. How about that one? All right, we just showed the most extreme correct version of equivariance. This is also equally varying. The difference being the points are not equally concentrated across X. All right, now they're more concentrated in the middle, which will be a lot more like your actual real-world data. Most real-world data isn't perfectly spaced around the x-axis. That would be cool, but not very realistic. So here are some perfectly reasonable equal variance demonstrations. This might not look it because you see like you're coming to, it's like a football shape, except there's not enough data out here to really say that the variance is too different than in the middle. Does that make sense? Right, if I randomly sample 4 points with the same data, or with the same variance, it could be anywhere in this range, and it is. Okay? Like I was saying, these are all okay when it comes to equal variance. All right, enough of that. So are these. The previous one had 300 data points. This one only has 50. With smaller data sets, actually that one looks pretty bad, but if you can see that, then I think you're okay to go. Okay to go, good to go. But in principle, each of these are constructed to be random variates of equal variance. Some of these look bad because they're just a small sample size. That one looks pretty bad. So this would be a great test question, actually. The variance is this large on this side and small on the other side. That one's randomly, but not equal variant. All right, what's the last condition we can check? Linearity. Can we check independence? Not really. If you're working with explicitly time series data, there are ways around that, but generally you just need to know that the data was gathered in a good, correct way, which usually means random. All right, is that linear? So on the left we have the scatter plot. On the right we have the residuals from a linear regression fit. Does the scatter plot look linear? Possibly. Does the residual plot look linear? No. Heck no. All right. There is a slight curvature in the scatter plot, which is you can't really see with the naked eye. But if you fit a line to it and check out your residuals, you very much see that there was curvature. Get a better example of it. There we go. Here's the opposite problem. This bows out to the top slightly, and you see that in the residuals now if you plot the residual plot. All right, perhaps this is just best called a pitch for why to look at your residual plot. Well, we won't go there. Well, here. Is that linear? Yeah. This is actually just about perfect. Another demonstration of what your residual plots hopefully look like. There's no evidence of curvature or heteroscedasticity for that matter. How about this one? Any nonlinearities? Is there any linearity? No, all right. So this is just random noise on x and y. So there is no linear relationship. Consequently, there's no nonlinear relationship either. All right, so here's my pop quiz. What conditions are violated, if any? Let's start with a slightly different question. Which one is most violated?
Normality?
No, normality.
Let's say normality. Notice the QQ plot very much stands out as non-linear. All right, we want this to follow the line. If it follows the line, we're hunky-dory. There's a little bit of heteroscedasticity going on here because I made it that way. But we got lots of problems. Yes?
Knowing, you would still say it looks bad.
Which one?
When you talk about heteroscedasticity.
Oh, So to your point, let's look at just that. So I'm going to randomly generate the same version of the data. Oh, that was not what I wanted. All right. Harder to say, right? Or so in this case, normality is the big issue. Okay. All right. Any questions on testing your assumptions through plotting? Yes, sir.
When you're doing a residual plot, do you have the fitted values on the x-axis or just like x values?
Good question. If you have a multiple regression model, you would have to choose one of your x's, in which case you want to go ahead and just put the fitted values there.
What if it's just a simple?
If it's simple in your regression, your choice.
Would it make a difference necessarily?
I certainly hope not. I would say not at all, but as we see here, even with randomly generated equal variance things, sometimes it doesn't look so equal, and there could be a case where they don't quite show the same thing. But 99,000 times out of 99,001 times, it should be good. All right, if no further questions, let's open this CARS data set and answer some questions. All right, so I downloaded the CARS data set here. These guys open the View tab so that you can view the data set. This data set's a little bit large. It has 29,000 rows. So we're just going to look at the first 6. I can look at the first 6 lines of a data set with the head command. Yes, ma'am.
Really fast. So for the linearity one, the one that we're looking at right now, is it supposed to be same equal variance or not?
How do you mean?
Like to check if it's linear, because that's the linearity not.
Yeah, so you can use the same plot to check linearity and equal variance.
Oh, okay.
In this case, the variance isn't great, and if you look into it, there's actually less variance below the axis than above the axis, which is a little bit weird. That's kind of like a yellow flag, maybe not a red flag. But in general, this is okay. I don't see any curvature in my residuals, and I can't see that the variance is drastically different at any section of the plot. All right. So if you can open the CARS data set, we're going to price used Mercedes. Specifically, what's probably the most dominant feature in determining a car price? Anyone? Anyone bought a car? Miles, right? How much you've used the car. If the car is brand new, it's going to cost a pretty penny. If the car is used, meaning it's been driven and the feature's worn out, then it's going to cost probably less, right? So mileage is probably going to be our #1 indicator. And our second indicator that we're going to look at is a little trickier, perhaps. But because these are nice cars, some of them may not have been driven so much, and some of them may edge more on being classic than new. Classic being a good thing in this case. So we're going to also include year in our model, right? Because I had a question earlier about interaction, several questions actually earlier about interaction terms. If we just put mileage and year in our model, then the difference between old cars with low and high mileage will be the same as the difference between new cars with old and high. Did I say that right? Old cars with low and high mileage, that difference will be the same as new cars with low and high mileage. However, if you have an old car with low miles, that probably is not a bad thing. That probably means it's a showroom car that has been on fancy display and is worth a lot of money. Right? As opposed to, as age gets older, we expect price to go down, and as mileage goes up, we expect price to go down. So we want an interaction term. So let's do that. So I'll show you this. My slides are in the wrong order. This is great. Go ahead and build that model. So download the CARS data set. Build a model that has an interaction between mileage and year. After you do that, please look at the residual plot. Oh, yes. Please model price using the interaction of mileage and year. Yes, 1 second, sorry. All right, try that again. Give me a general head nod or a thumbs up or something when you're done. I'll be able to pace the class. It'll take another 90 seconds or so. If you need help, please don't hesitate to raise your hand. After all your questions will keep us employed. And I guess it works.
Why is my audio
So your R is probably going slow because this data set is
massive?
just the same. Yeah, your R may be going slower than normal because this data set is very large. You're welcome. Maybe I should post a reduced size version. But you can look at the first 6 rows. I would not. I wouldn't do that here. Because there's 30 columns in here and 1,000 rows.
That's not.
All right. Is this what you get for your residual plot? What's wrong? Yes. Oh, go ahead.
I don't know.
If your residual plot doesn't look like this, please shoot a question to these guys. They can help you fix your code. But in general, for those who got this, what's wrong with our model? Some outliers? Yeah, most definitely. You probably got some cars in there that have been used by a driving service and they have 400,000 miles on them. What else? We definitely have an equal variance problem. We probably have a linearity problem, but our equal variance problem is so extreme we can't even tell if there's a linearity problem. Question? Okay. One of y'all want to talk to her? If you look at the normality plot, it doesn't look much better, does it?
No. There it is.
So where should we start? If you recall from lecture 17, probably didn't remember the class is lecture 17, but that's how you can find this in the slides. The first tip you're given is if you have lots of issues, first try transforming Y. Alright? If you have single linearity issues, you can transform one of your x's first. But in general, the best place to start, this is now erring into Jared's opinion, but generally the best place to start is transforming Y. So go ahead, redo your same model, but now with log price.
I am. I'm thinking I could just do that.
Yeah.
So even if there's a slide.
I was going to type it in the model before I was so really interrupted. It's just a lot.
Yeah, I can see the whole screen.
No, I mean,
Oh, for linear.
With this one here. Oh, you're right.
You can do that if you want. Long recognition is useful, but horizontal.
below.
Okay, so you rule that you just stop.
We'll do that. For only some functions.
So you can do
I
this.
don't know.
Breaking about like it's weird if you
Look, man, I don't know. I don't know how to
Well, I
see
guess
it.
that's a bigger issue if you have logging.
Weird that it's different
Let's say
instructions.
it's logging X. If you take the log outside of this, variables plug in, you're changing price.
Yeah, that's probably how you price it.
Log here. Put that in the log.
A little more.
Wait, so we can put it
So like, next value is
So for linear,
You're looking for the randomness of residuals along the system.
along the system. Okay.
The residuals should be
Along
you know, I don't have
Okay.
Exactly.
I would want you to
That?
You can always change it outside and plug it in.
Okay. Gotcha. Yeah.
All right, did you get a chance to log it?
So it's big.
How does it look? Beautiful, right? Oh! All right, is it perfect? It's still a little wiggly. Is it a lot better?
Okay.
Yes. All right.
Thank you.
So good to take the log of y first and then try other things. So just to restate that, so this is a really good slide. So after you try transforming y, if your issues aren't fixed, so clearly the issues are better. So we should take the log of y and then continue onward. And this is slide 25 from the lecture 17 slides, which are online. If you don't want to type all this right now. But yeah, next, try transforming. If you still have issues, you can try. That's just not the one I was looking at. This one. If your issues still aren't fixed, you can try transforming your predictors as well. There is no particular rule for what works when. There are some good suggestions. You can find those all sorts of places. But sometimes you need trial and error. Right? So if you have one x and one y, you could try log y, log x, both, and just look what happens. Yes?
For the example, or I don't know if you're able to say this or not, but would we be told what transformation to use, or do we have to try different?
Depends on the question. So if the question asks, what would be the change in log price, then you know you want a log price. If the question asks, how do you fix this, then that's up to you. Okay?
looking at the QQ plot for change price with the logarithm.
No, sorry. I'm telling you, yes. If you change the price with log and you look at the QQ plot, we still have normality issues. Now the shushing was more comical than anything. I just didn't want to show that yet because we're not going to address it today. But yeah, the model still needs help. It still does not meet the normality condition.
So you can log all even x and y.
Sure. And we'll get to the only issue with that in just a moment. So this is a slightly different example, but I pulled a different example in so you don't have to do this with the interaction term. Let's say we have a model of log income. So this is your starting income after graduation. It is actually pretty reasonably modeled by 10 plus 0.03 times your GPA. I don't know if that's true, but if you plot the curve, it at least makes sense. Right? This basically means if you have a 0.0 GPA, you start making $20,000 a year. If you have a 4.0, you start around 75K. Anyway, that's not the point. The point is, what's your change in income if you increase your GPA from 3 to 4? It's not 0.03, right? Your change in log income is 0.03 because that's the definition of a slope. If we increase GPA by 1, which is 3 to 4, the change in your response variable is the slope. So 0.03 is the change in log income. Who wants to get a log income someday? All right. No, we all would like an income someday. So what do? For the sake of time, I'm not going to have you work it out on pen and paper because it's not very fun. Well, I mean, it's fun if you enjoy algebraic math. But you exponentiate both sides. So you get income, right? Because we take e to the something. That's called exponentiating. E and log cancel each other out. So the left side just has income. On the right side, we now have e to our model. So that's e to the 10 plus 0.03 times GPA. Well, we can split that apart by rules of exponents. We now have e to the 10 times e to the 0.03 GPA. And then we're going to need to take a difference between x equals 4 and x equals 3. And you can simplify, kind of, to this beautiful construction. Or, as mentioned earlier, we can take a predict.lm statement, tell it GPA equals 4, minus the same predict.lm statement, but with GPA equals 3. You're welcome to do either on the exam, whichever you're more comfortable with. So, to your question, any questions on here? All right, so to her question earlier, what if we take the log of both x and y? You can certainly do that. There are some wonderful things about log-log models. So kudos to those of you who on that homework question said, I like log-logs because it maintains some interpretability as opposed to log square root. That is not something you need to retain from this course, but maybe you need it in your job later. We can certainly say log income. If this fixes, I mean, the whole idea is to fix the regression assumptions, right? Because if you don't fix the regression assumptions, your p-values mean diddly squat. Okay. This model has about the same effect. Same curvature as the other model, gives you starting salaries in reasonable ranges. So let's say I'm now interested in increasing my GPA by 10%. All right, so we're not going from 3 to 4, we're, let's say, going from 3 to 3.3. Yeah, it's not 0.8. This isn't simple again. And in fact, we have to do 2 changes. All right, so we exponentiate y, so we get e to our model. But inside our model, we have a log, so we can split up the addition, take out the exponent, and then e and the log cancel. So we get e to the 10 times your GPA to the power of 0.8. Then to get the 10% change, which is from 3 to 3.3, or from 2 to 2.2, right? You take e to the 10, 3.3 times 0.8, minus e to the 10, 3.0 times 0.8, or 3 times to the 8th, to the, I can't say that for the life of me. 3 to the power of 0.8. Yes, ma'am. Yes. Everything will be posted on Canvas, GitHub, or YouTube as appropriate. Okay. So once again, you can do this. It's correct. I'd have to double check the math to make sure that's okay for every 10% increase. Questions should be appropriate on the exam to be accurate for any type of 10% increase. But when in doubt, once again, you can punch it into predict.lm, GPA of 3.3 minus GPA of 3 in your equivalent statements, and that should give you the answer. Yes, sir.
So when you do the 2 predict.lm methods, you don't have to do the reverse. That number that you get is after exponentiation.
Ah, good question.
Because it doesn't say it.
Man, all right, yes, you're exactly correct. So I'm going to go back and correct this on the fly. This gives you the log income, right? Whew. All right. The great thing about doing transformations, you can fix your regression assumptions. The hard thing about doing transformations, you have to be good at bookkeeping. So remembering what you're doing, because I very obviously, right here, have screwed up. All right. Thank you. Yes?
Transform the, to exponentiate the GPA too.
Great question. So not like I have it on here. And that's what the double asterisk, triple asterisk on the bottom is. So if you created a new variable in R, so let's say you went and created GPA underscore ln to represent the natural log of GPA. Great thing to do. It keeps it very clear when you're plugging that in. If that's your variable in your regression model, this statement here won't work because you don't have GPA in your model. You have GPA ln, right? In that case, yeah, you need to go take the natural log of these pieces and plug it in. However, if you put this in your model, right, if you typed the log function straight into the lm function, R will be expecting GPA, not log GPA.
So you would
Here? No, so if I was doing this as you were saying, I would type something like this. Okay? Let me show you the difference in R just real quick. The difference being this, what are we doing? Income. That's not going to run because there's no data. Versus this. In one case, R is going to be helping me. Here, you're putting GPA and income into the model. Here, you're putting log GPA and log income into the model. And that's what R will be expecting. This version doesn't work for all functions. If you're squaring something, that won't fly. You can't square something inside of an ln statement. I wish I could give you an exhaustive list of which ones do work. That might be on Google somewhere, but I don't know. Okay? Given that logs are what we usually do, this is very advantageous. I would use the first one personally. Because then R will be expecting GPA in the model, not log GPA, which is a lot more user-friendly. It's not. Sorry? I can't hear the back half of your question.
So like, when do we use the log function versus just not using it in the data set?
Great question. So here we have a homoscedasticity issue. Actually, we don't have homoscedasticity, so we have heteroscedasticity, right? And usually, quite often, the great way to fix that is take the log of your response variable.
Okay, so if you take the log and it's still like not equal variance, we just say that the data is not equal variance.
You can now try transforming your x variables.
And we just keep going until.
There should be a foreseeable, especially on the exam, there'll be a foreseeable end to that process. In the real world, if you're an analyst, it may just be your data's bad. You're not bad as in inappropriate or incorrectly taken, but it might just be that a linear model is not going to work for the data at hand. Yes, sir? Me personally, as Jared Fisher, yes. The official statement from the course is here, which basically says the same thing. Yes?
Will we have to transform both x and y at the same time, or it's just going to be one by one that we should?
I would do it one by one. A, to avoid complication. B, logging y might fix all your issues, and then you don't have to do both.
But we won't be asked that.
If you're asked directly to do both transformations at once, I would do it. But typically, you're doing these phases one step at a time. Like with regression, we often remove and put in and take out one variable at a time. It allows you to see the effect of individual pieces. Yes, sir?
With regards to the slide back question. Well, yeah, so the R script, I understand that, but in this case specifically, what would you put in for model? Since we don't have any data, we just have like 10 plus 08.
Oh, in this case, you're going to have to write out the algebra specifically like this. If you had built a model and his name was model, you could plug that in.
Right.
I wrote this as a pseudoscript. Yes?
But can you plug that into R and find an answer?
This piece right here? Or this one right here?
Yeah, that one.
I certainly can. I'm going to have to adjust it a little bit. Because it's not going to take my exponents or my e's. But I can certainly do this. E to the 10 times 3.3 to the 8, 0.8 to the 10 times 3 to the 0.8. Nope, e is not a thing because I'm smarter than that, but I'm thinking on my feet. Everyone makes mistakes, right? That's why you get multiple chances. All right, 4,200. Any other questions? I got one more slide for you, and then we'll wrap up and just have general Q&A. All right. So R squared is the best thing to look at for your model, right? Sometimes. Good response. R squared tells us the percent of y that's explained by x. Or more specifically, the percent of the variation in y that's explained by your model. Okay? By all of your x's, right? You have lots of x's. However, mathematically, we can go through the calculation if you really want to, but when you put a new variable into a model, R squared cannot go down. Right? Even if your variable is complete noise, totally random, has nothing to do with your data set. Right? If we took, the whole student GPA problem and we put in there what you ate for dinner June 3rd, 2003, that could have something that increased the predictability of your model a little bit. And if nothing else, it's noise and it'll have a zero coefficient, right? So zero coefficient means R squared stays the same. Some type of coefficient means R squared's going up. So R squared can't go down even if you put garbage into your model. Garbage is the worst case scenario. What if you put a variable that's not really important, but does have something to do with things? That's when things get hard, right? Is deciding what makes a variable good or not. But if R squared's always going up, we can't really use that as a decision criteria because we'll end up just putting all the variables in our model. So there's some alternatives. We have adjusted R squared, AIC, and BIC are three that we've discussed in the class, each of which has some form of penalty for additional variables. In other words, you're trying to balance the size of your model, the complexity of your model, with how well it explains why. So in general, R squared going up is good. Adjusted R squared going up is good. And if you look up AIC and BIC inside R, you want them to go down. All right? The lower AIC, so like negative 600, is better than negative 500. I believe you just had a question on your homework about that, right? We can use these with forward or backward stepwise regression, like you just did in your homework, which I believe looked at AIC and changed variables back and forth and to improve AICs. That may have been the subset selection, actually. Or was that BIC? Anyway, point's the same. You use these to try to make decisions about what to include in your model, especially when things are waffling on the border between significant and not. Yes, ma'am?
Wait, so are you saying that if you add another variable, your adjusted R squared might actually go down?
Yes, absolutely.
Okay, that's possible, but not for the multiple.
No, multiple R squared cannot go down. Yes?
On homework 8, when we created like the plot with the BIC,
Mhm.
it had like, there were like negative.
White and black blocks?
Like
Yeah.
I don't know what I'm trying to say. It's easier if I show it to you, but like there's some of them showed like if you use like 4 variables in your model, it gave you the same BIC as if you use like 5 other variables. But the answer on the homework was like the one with 5 variables had the lowest BIC. They all have the same.
It looks something like this. Oh, that looks a lot fancier than the one I remember. It looks something like this?
Yeah, but on the homework, like all of the like top BICs were negative 660.
Right.
So like which one's the best mix?
I'm really perplexed why this doesn't look just like that. Yeah, so that plot's particularly tricky because you end up getting a bunch of models that are negative 660 point something, and it cuts off the decimals. That's what happened there.
There's always just one.
Right, there's one on the top. And you can look on the bottom, it should say negative 580 or so.
Yes.
Yeah, so that shows you the direction of the axis. So just go straight up at the top, that's the melody you want. The thing to be careful with is that first block is the intercept and not actually one of your variables. Okay, yes?
Does that eliminate multicollinearity? BIC, the lowest BIC?
BIC is not particularly calibrated for multicollinearity. There's probably a degree at which it will help with that because if you add in a multicollinear variable, that's so correlated with one of your other ones, it won't help your BIC very much. It may actually hurt.
How does the low BIC
Low BIC means you've done well to fit your model, but not put in too many variables as to penalize it excessively. So essentially what this is doing is it takes a negative, not quite R squared, but it's called the log likelihood. So it negates the fit of your model, so that's a negative value, and then it adds points to be a penalty. And so the more negative, the better, because you have low penalty and high explanation. Would it make sense if they flip the negative sign there? Yes, but they don't.
Okay, so like you have like the correct number of variables.
You have an optimal number of variables when it comes to the AIC. Now, if you take the AIC, it might differ slightly, because they're just slightly different definitions. Yes, sir?
So on the practice exam, there's more questions about AIC and DIC, stepwise regression, forward, backward. And that's on the practice exam. What should we kind of so I'm curious as to
I believe everything.
I guess I'm kind of related. I'm trying to find out where we do like problems with that, or like where we could something that actually something over the
I don't know if someone had problems with that.
All of them? No.
Small.
Oh no, I know how to do it.